Ladies and gentlemen, welcome to the video lectures on EC 393 Digital Signal Processing. This is lecture 2 and the lecture is divided mainly into two parts. In the first part, we shall try and solve a couple of numerical problems on the continuous time Fourier series that we have learned earlier. And in the next part of the lecture, we shall start our next topic, which is the discrete time Fourier series. Okay, now hoping all of you are well, let us dive deep into the topic. First of all, let us solve a numerical problem. We are to find the Fourier series of a given signal. Let us mark it as example Let us mark it as example 2. I'm sorry. Okay, the pen seemed to give up the ghost. Example 2, where the problem states that we are to find the exponential Fourier series representation of the given signal. Now let us see what the signal looks like. If this along here is our time axis marked by t, and this is the y-axis, which is marked by f of t. The function here looks something like this. And similarly on the other side, each of the pulse having an amplitude similar to the previous one, and the signal is repeated every pi times. Here it will be 3 pi and it will go so and so forth. Here it will continue in this direction, so and so forth. This becomes negative of pi, this becomes negative of twice pi, and consequently negative of thrice pi. So this is the signal given. Now let us come to the solution. First of all, we are to determine the time period of the signal. So the time period that is T naught is given by pi, because as I have said, and as it is quite clear from the diagram, that the signal repeats itself after every pi times. Very well, so the angular frequency omega will be twice pi over pi, that is twice pi over T naught, which is the formula, which equals to 2. Then let us go ahead and define the function f of t, which is sine of omega t. Now the question arises, how come this is a sine function? If we look from 0 to pi, we see that the function behaves like a positive cycle of the sine function. And if you can recollect from your memory, while we have studied the electronics, I don't remember the course code, in your electronic course, you might as well have seen this type of curve in the rectification sequence. So when we put a sine wave through a rectifier made up of a couple of diodes, the signal becomes something like this. So this is nothing but a rectified sine wave, and since we are going to take the integral in order to determine the Fourier coefficients over 0 to pi, so what goes after pi to 2 pi doesn't concern us if it is negative or positive. The only concern is that 0 to pi the signal behaves like a sinusoid and in fact a sine wave, so we can write f of t as sine of omega t. Now then, let us go forward and solve for the Fourier coefficients. Solving for the Fourier coefficients. As we have seen from the previous lecture, the formula is C of n 1 over t naught, which is the time period, and the signal goes from 0 to t naught, f of t e to the power minus j n omega naught t, rather omega t dt. Now, replacing the values from the replacing the values of the time period and the function itself, we get 1 over pi, which is the time period as mentioned over here, and the limit goes from 0 to pi, and the function f of t, which becomes sine of omega t, and the rest is quite same as before, minus j n omega t d of omega t. The limit changed from d of t to d of omega t because now, since in the x-axis we have omega t as our abscissor, so we shall be differentiating with respect to omega t rather than t. Now, once again, we shall go to the Euler's relation. And the relation states that something like this: cosine of theta plus j sine of theta equals e to the power j theta, and consequently cosine of theta minus j sine of theta equals e to the power minus j theta. Now, if we subtract both the equations, this becomes minus, this shall become plus, and minus as well. So adding these two terms, it becomes 2j sine of theta equals e to the power j theta minus e to the power minus j theta. And upon simplification, sine of theta becomes 1 over 2j e to the power j theta minus e to the power minus j theta. Now, we have derived an expression of Euler relations in terms of sine theta, and what we are going to do now is replace this sine theta with this type of expansion. So the above expression becomes C of n equals 1 over twice pi j 0 to infinity e to the power j omega t minus e to the power minus j omega t, and this term over here, which is e to the power minus jn omega t d of omega t. Now this twice j is nothing but this term over here, and theta in our case is omega t as shown over here. Theta becomes omega t, so the angle is j omega t rather than j theta. Now moving forward upon further simplification, the equation becomes 1 over twice pi j integral of 0 to pi e to the power j omega t 1 minus n. That is, we are multiplying these two terms and taking j omega t as a common factor from both this term. I mean this and this term. And similarly for this and this term again, on multiplication we get e to the power j omega t 1 plus n, and the whole thing is integrated for d of omega t. Now, as per the property of integral or integration operator, we can divide these two terms into two integrals, and it becomes 2 pi j taken as common over 0 to pi e to the power j omega t 1 minus n d of omega t minus 0 to pi e to the power minus j omega t. Sorry, there will be a minus over here. 1 plus n d of omega t. Now, upon solving this two integral, or in order to solve this two integral, we can write c of n becomes 1 over twice pi of j, which is a common factor for both the integrals. And I'm sorry, we are now solving the integrals, and the integration of e to the power something is e to the power something, that is e to the power j omega t 1 minus n, and divided by its common factor j of 1 minus n, or rather I should say not the common factor, the factors that are not associated with the integral operator, that is omega t. We put down the limit from pi to 0 or 0 to pi, and same goes for the second term, which becomes e to the power minus j of omega t 1 plus n and j of 1 plus n. Similarly, putting the limit from 0 to pi. Now, putting the limit in the equations, we get the first term to be e to the power pi j 1 minus n. That means here omega t is replaced by pi at first, and then omega t minus omega t is replaced by 0. Upon replacing omega t with 0, this term becomes 1, and the denominator remains as it was, and I'm sorry, there will be a minus over here as the factor. The minus will also come in the denominator. Now multiplying these minuses, this becomes plus. This expression becomes e to the power of minus j omega t 1 plus n, I'm sorry, not omega t, pi 1 plus n, and the denominator remains as before. So let me write it again for your edifications. The expression is e to the power pi j 1 minus n minus 1 j 1 minus n plus e to the power minus pi j 1 plus n over j of 1 plus n. No mathematical changes from this line to this line. I have written it only for the clarity. Now, first taking for the numerator, that means I am taking this term over here. I'm sorry, this term over here. Well, what do you say? Both of them decided to die. So, dire times, ladies and gentlemen. I'm talking about this term over here, and I've made a mistake once again. There will be a minus 1 over here and here as well. So, now working with this term, we are trying to solve it as the Euler expression, where t to the power j 1 minus n becomes e to the power pi j minus e to the power pi j. This is basic property of exponents, where we can divide it up and write it like this. Now, expanding these both terms as the Euler relation, we get cosine of pi plus j sine of pi minus cosine of pi n plus j of sine pi n. Now cosine of pi is always negative 1 and sine of pi is 0. So this expression becomes minus 1 plus 0. Now here we need to be careful, because n can be both positive and negative, I mean odd or even number. But when n is odd, for let me write it down, for n is odd, we get cos pi of n to be equal to minus 1, and for n is even, we get cos pi of n equals 0. So this expression becomes minus 1, 0. For odd, this becomes minus 1, that is minus of minus 1. This will always be 0, whatever may be the case. 0, which equals minus 2. This is for the odd case. And for the even case, for n when it's even, we get it minus 1 plus 0 as before. Here we get minus, this minus becomes plus, and this becomes 0. This becomes minus of I'm so sorry, ladies and gentlemen, there has been a mistake. Cosine of pi n when n is even is equal to 1, not 0. So this becomes rather 1, and plus this will always be 0, so it becomes minus 2. Now similarly, upon solving for this expression, we get e to the power minus pi j 1 plus n equals e to the power minus pi j plus e to the power minus pi j of n, which when expanded to the Euler's relation becomes something like this: cosine of pi minus j sine of pi, plus this term becomes cosine of pi n minus j sine of pi n. Now once again, this term is always minus 1. This becomes 0, so we can write minus 1 minus 0, and when n is even, we can write this term to be 1, and this is always 0. So it becomes 0 for n equals even, and for n equals odd, this too remains as it was, minus 0. This term in terms becomes minus of 1. So here we get minus of 1 minus 0, and the result is minus 2, solving for n when it is odd. Now as you can see, we will have two values of c of n, one for the odd values of n and one for the even values of n. So let us first solve for the odd value. C of n odd equals 1 over twice pi j. Putting the value in this expression becomes 0 minus 1. As you have seen, this expression is 0 when n is odd. The denominator remains same as before, plus this becomes minus 2. The minus 1 will remain as it is. The denominator remains the same. Now upon further simplification, we can write this to be twice pi j minus 1 plus n minus 3 1 minus n j of 1 minus n and 1 plus n. Just adding these two fractions. These in turns become twice pi j minus 1 minus n is 3 plus 3n and j of minus n 1 plus n, multiplying with the factors, and finally we get 1 over twice by j 4 plus 2n j of 1 plus n 1 minus n j as it was. And now Cn odd then becomes 1 by twice by j, taking 2 as a common factor, rather minus 2, this becomes 2 plus n j of 1 plus n 1 minus n. This 2 and this 2 will cancel out, and what remains is that 1 over pi, this j and this j will multiply and becomes j squared, and we know that j squared equals minus 1. So plugging in the value of minus 1, we get, here it becomes minus 1 plus n Now, upon multiplication of the numerator and denominator with minus 1, we get the final result, which is 1 over pi 2 minus n. I'm sorry, this seems to be minus. If we take minus 2 common, this becomes minus and this becomes minus as well, over 1 plus n and 1 minus n. So this is the odd coefficient of the Fourier series. Now, solving for the even coefficient, we get C of n, which is even, equals 1 over pi over twice by j minus 2 and minus 1. Minus 1 from the expression, minus 2 when the value is even, the first expression yields the value of 2. The denominator as it is, j of 1 minus n plus 0 minus 1 j of 1 plus n. Now simplifying once again, twice by j, this becomes minus 3 1 plus n minus 1 1 minus n j of 1 plus n 1 minus n. Just adding the two factors, then we get twice by j, this becomes minus 4 minus twice n j of 1 plus n 1 minus n, which equals twice by j and 4 plus twice n, and multiplying this minus, which is taken as common, to this j minus j 1 plus n 1 minus n. Now once again, if we take 2 common from the numerator, taking 2 as a common factor from the numerator, this becomes 2, this becomes plus n, this remains the same, 1 plus n 1 minus n, and cancelling this 2 and this 2 and multiplying once again j and j, we get 1 pi 2 plus n 1 plus n, and 1 minus n. Now, as we have seen, Cn even will become 1 over pi 2 plus n, 1 plus n, 1 minus n, and Cn odd in turn becomes 1 over pi 2 minus n, 1 plus n, 1 minus n. Now finally we get the expression f of t to be summation of n, which goes from minus infinity to infinity, c of n e to the power minus j n omega t, which we can write in terms of the even and odd coefficient. N goes from 0 to infinity, and n is even, which becomes Cn even. That means you need to put this value over here, e to the power j n omega t, plus n, which goes from 0 to infinity, and n in this case odd. We get Cn odd e to the power minus j n omega t. So this is the required Fourier series expansion of the given signal that we have seen, and upon various values of n, when n is equals 1, 3, 5, we get the odd coefficients, and putting the value of n from 0 to 4 and so, we get the even value, and we can expand the series, which is not required, and I hope you can do it by yourself.